So let's think about an example. Let's take the two vectors u with entries 1, 2, 3, and v with entries 4, 5, and 6. So if we want to find all of the vectors w that are orthogonal to u and orthogonal to v, we start out by forming the matrix A, whose columns are u and v. We can take the transpose of this matrix, so we'll have columns 1, 4, 2, 5, and 3, 6. To find the null space of the transpose, we need to row reduce. We can ask Sage to do this, and it will give us the reduced row echelon form 1, 0, 0, 1, minus 1, 2. So this tells us that the set of vectors in R3 that are perpendicular to u and v form a line. And this line is cut out by the equations x equals z and y is equal to minus 2z. So of course we get a line, L, consisting of all vectors x, y, and z, such that the x-coordinate is z, the y-coordinate is negative 2z, which we can express as the span of the vector 1, minus 2, 1. Now it's worth mentioning that there is some geometric significance to this computation. If we row reduce the matrix A, then we'll get the two columns, 1, 0, 0, and 0, 1, 0. This tells us that the two vectors u and v span a plane. So if we draw a plane, and this plane will pass through the origin, then we can think about L as coming directly out of our plane. And in fact, this actually gives us a really handy way of specifying a plane. So we have a vector, let's call it n, with entries 1, minus 2, and 1. This is a basis vector for L. So if we're given any vector w, which is a linear combination of u and v, which necessarily lies in P, then we can think about w as being a vector that is perpendicular to this vector n. So if instead of expressing n in terms of u and v, let's write it in terms of the three standard coordinates x, y, and z. In order for this vector to be perpendicular to n, it must be the case that the dot product of n with w is 0. So, of course, if we compute this, we just multiply the coordinates together, and so we see that we can express the plane P, which was the span of our two vectors u and v, as the set of all vectors which satisfy the equation the x-coordinate minus twice the y-coordinate plus the z-coordinate is equal to 0. Or more simply and more commonly, you'll see this written as P is just the set of solutions to the linear equation in three variables, x minus 2y plus z equals 0. So as you might guess, this set of perpendicular vectors is actually relatively important. So we're going to give this a name. If v, which is the span of the vectors v1, v2, down to vn, is a subspace of Rm, then we define the orthogonal complement to be this space of perpendicular vectors. So we can think about the space V as the column space of the m by n matrix A, whose columns are v1, v2, down to vm. So this tells us by our previous observations that v perp, the orthogonal complement, is equal to the null space of the transpose of A. But if we think about V as being the column space of our matrix A, then we can rewrite the left-hand side of this equation as the orthogonal complement of the column space of A. So the orthogonal complement of the column space of A is the null space of the transpose of the matrix whose columns are the basis of this space V.